Alright, today we were looking at the atmospheric circulation. So at this point you should have your notes out on the atmosphere. So the essential question that we're basically asking here is, what is wind? So that's the question we're trying to define in today's notes. Okay, the definition here is the horizontal flow. So horizontal means it's going side to side, and it's going from high pressure to low pressure. So it starts off at a high pressure and it moves towards a low pressure, and that's what wind is. Okay, these pressure differences are caused by uneven heating of the Earth's surface. So if we look at the Earth, so here's the Earth, and then the sun is way out over here. Okay, the light comes in and it hits the Earth like this. That means that where the sunlight hits the Earth directly, that area is going to be the hottest. So right here is the hottest, and then as you go away, so as you go towards the poles of the Earth, you're getting less direct sunlight, so it's actually a little bit colder. So we find that this area right here, where the Earth gets most direct sunlight, is where it's going to be hottest. This uneven heating that we just mentioned causes pressure differences that we'll talk about in a little bit. So basically what we get from this is that the solar energy, so the energy that comes from the sun, is what drives and produces wind. So we have wind because of the energy from the sun. Okay, this leads us to the concept of a convection cell. So remember from last time that a convection cell is kind of like water boiling, where if we put water in a pot and we put it on the stove, so there's a little fire going on underneath it, then remember the water gets hot down here in this area first. Once it gets hot, that water is going to rise, but then the air up here is cool, and so the air is going to cool off the temperature. So as this temperature gets colder, that water is actually going to fall back down. But once it gets cold or warmer, once it gets towards the bottom of the pot, it starts warming up again, and so it warms up and then it starts to rise up, and before long we're going in this continuous circular pattern, and that is called a convection cell. Okay, this is the same process that's occurring on Earth, on the surface of the Earth. We have sunlight that comes in, so sunlight comes in, direct light comes in from the sun, makes it really warm, and this would be right along the equator. So the equator is where it gets really warm. What happens is the land right here at the equator gets warmed up. Because it's warmer, that hot air is going to rise. So the hot air rises, but once it gets up to the top, it has to push the air out. So any air that's up here is going to get pushed away, and so we have the air moving out this way. And because this is the equator, it's actually going the other way as well, but we're just going to focus on one side for now. So the air gets pushed this way to the left, and then as it gets away from the equator region, it starts to cool off, and as it cools, because it's less dense, it starts to fall down, and it goes back towards the Earth. Now, because the air is being pushed down, it causes it to go to the right. Okay? And so this, just like we had in the boiling water, is forming our convection cell. So the wind is continuously moving in a circular pattern, and it's all happening because sunlight from the sun warmed this region up and caused the warmer air to rise and then circulate in what we call a convection cell. Alright, here's a quick check for you. The question is, how does energy from the sun drive the movement of the air? Okay, the hint that I gave you, this is similar to how water moves when it boils. So I want you guys to take 20 seconds of think time, and then I will have you share with your partner. So 20 seconds to think about it. Go. Okay, now turn to your partner and share with them your response. Okay, go ahead and come back up here, and then we're going to move on with the notes. Okay, the next item we're going to be looking at is something called the Coriolis effect. Now, the Coriolis effect is caused because of the Earth's rotation. So if I were to draw the Earth right here, and let's say the Earth is rotating this way, then because the Earth is rotating on its axis, so the axis of the Earth is like this. Actually, it's a little bit tilted. The axis of the Earth is a little bit tilted like that. So the Earth is rotating. Because of that rotation, that influences certain ocean currents and wind currents, as we're going to see in just a minute. First, we see that if an object is not attached to the Earth, then it follows a curved path. So, for instance, this would include air or water because they aren't physically attached. They are resting on the Earth, but they aren't attached to the Earth. That means they wouldn't flow in a straight line. So the air doesn't flow in a straight line along the surface of the Earth. Instead, it follows a curved pattern. And that is all caused by the Coriolis effect. You'll see that question on several tests. That's one that you'll need to make sure you understand, is that because of the rotation of the Earth, certain wind patterns or certain patterns are curved and they don't follow in a straight line. We see that there are two general patterns from the Coriolis effect. If it's in the northern hemisphere, then it's deflected to the right. That means it curves to the right. And if it's in the southern hemisphere, then it's curved to the left. So here's the Earth. I'm going to draw the equator. So here's the equator right here. Now, in the northern hemisphere, we said that the wind patterns are deflected to the right. Now, we have to kind of visualize the Earth because we don't look at this from our perspective. We have to look at it from the perspective of the wind patterns. We'll see this in a little bit, that the air is actually flowing towards the equator. So because and this is in the first latitude band, so we'll get to latitude bands in a minute, but in this small section, the wind is actually flowing towards the equator. Now, you notice here I have pretty much straight lines, but wind doesn't flow in straight lines like this. So what happens is because of the Coriolis effect, those all get turned and they're curved slightly to the right. As a result, if I was looking at it from the direction of the wind, I wouldn't be going straight, I would be curved to the right. So I know from your perspective this looks like the left, but you have to do it from the perspective of the wind blowing. So imagine that you're in a car traveling in this direction, then you would be traveling down towards the bottom of the Earth, so curving right would be going in this direction. Now, the similar thing happens on the other side of the equator. So if we draw another latitude band, and again, these will make more sense in just a little bit, the air is traveling towards the equator, but notice it does not travel in a straight line. It instead travels to the left. So this is easier for us to visualize. The air travels up, but then because of the Coriolis effect, it turns to the left. Same thing here, and same thing here. And that's the Coriolis effect. So as we just learned, global wind belts do not follow a straight line. Instead, they're curved because of the Coriolis effect. This produces three convection cells. We already saw the convection cell earlier. That's a circular pattern of movement. Now we're going to look at how those convection cells relate to the Earth as a whole. Okay, further, each convection cell correlates to a wind belt known as its prevailing wind. Now, you'll want to pay attention to these diagrams and you'll want to label them on your notes. The diagram on the left, this shows pressure belts. So these are pressure belts. And then the diagram on the right, these are the wind belts. So we'll look at each of these, and this is actually what we'll be diagramming in our notebooks in just a second. Alright, so now go ahead and take a minute, get out your interactive notebooks, and turn to page 36, where we will be diagramming this, and just make sure that you add color to this. If you don't add color to it right now, that's fine, but make sure you shade this in later in order to complete this page. Okay, this is our diagram on global winds. So the way we're going to start is fill up most of your page and draw a circle of the Earth. Now, you don't want to take up too much room because we do need to have a little bit of room on the side. And then the first thing we're going to do is draw our latitude bands. Okay, the Earth is broken up into different latitudes and longitudes. So we're going to focus on latitudes today. So the first latitude is where the equator is, and this goes straight through the middle of the Earth, and that is at 0 degrees latitude. That's also called the equator, as we mentioned earlier. Now we go up. The next one we have is about 30 degrees latitude. We have 60 degrees latitude. And then the final one up here at the North Pole, this would be 90 degrees latitude. Now, just how we did on the northern hemisphere. Now, I say northern hemisphere because hemisphere means the Earth is divided into two sections. Here's the northern hemisphere, here's the southern hemisphere, divided into two sections. The southern hemisphere is exactly the same, so everything we do in the northern hemisphere can be mirrored on the southern hemisphere. So for instance, if 30 degrees north, so I'm going to add north to these to show that we're going north. If 30 degrees north is up here, then this would be 30 degrees, but instead of going north, we went south, so this is 30 degrees south, 60 degrees south, and then finally we have 90 degrees south down there at the South Pole. So those are the different latitude bands. Now, to show where light hits, you don't have to highlight this on yours, but I'm going to highlight it on mine to show what happens. The sunlight is hitting, and we mentioned this earlier, that the direct sunlight hits right around here at the equator. So this is where it generally is the warmest part because we have direct sunlight right here. Now, because the sun is heating that region up, that causes the warm air to rise. Now, I'm going to draw this on the side over here, so it's easy to see. But you just have to remember, whatever I draw here, this is on the surface of the Earth, so this would go in this entire band. But I'm going to show you here so we can see what happens. Now, when the hot air, when the sun is heating this region, that means the hot air on the surface of the Earth is going to rise. So this hot air is going to rise. And remember, as it rises, it's going to push any air that's over here away from it. So because it's pushing air away from it, that air can only either move down or it can move up. Now, as that air gets away from the equator, it's going to start cooling off because the equator is the warmest part. So as that air leaves the equator, it cools off. And we know that cold air will fall because it's less dense. So that cold air is going to fall back to the Earth. And then once it falls back to the Earth, it's going to push the air in two directions. It's going to push the air this way, and it's going to push the air back this way. So now we start to see this circular pattern forming, and remember this circular pattern is called a convection cell. So this is what we looked at earlier, called a convection cell. So the hot air, we'll go through it again, the sun warms up this part of the Earth, the hot air rises because it's less dense. So I'm just going to turn the paper real quick so you can see this. This is still the surface of the Earth, so the hot air is rising because everywhere on the surface going away from the center of the Earth is rising. So hot air rises, and then as it cools, it gets pushed away, it pushes air away, and then as it cools, it falls back to the Earth, and then it keeps pushing the air back, and so it goes in a circular pattern. Okay, so now this pattern influences the next pattern. So in the same way, the air gets pushed this way, and as it gets here, we start to see these circular patterns that start forming. So the air flows in the same motion. So air is flowing here, it's falling here, it's going in a circular pattern. So as it moves along the land, it's warming up, okay, and then as it goes back this way, it pushes the air back, and it keeps going in a circular pattern. And then finally, we have one more band. So you notice that the arrows always move side by side. Okay, so these arrows aren't moving in opposite directions, they're moving in the same direction. And so then it goes over here, falls back down, and then it moves back here, and those are the 3 convection cells. So we have convection cell number 1, number 2, and number 3. So you remember from the slide before this that each hemisphere has 3 convection cells. Now, I drew them here, but remember this convection cell is happening all along this band. Number 2 is happening all along this band, and number 3 is happening all along this band. Sorry, you probably couldn't see that. Number 1 is happening right here. Number 2 is happening right here. And number 3 is happening right here. So it's not just on the side how I drew it, but it's happening over the entire surface of the Earth. Okay, now we're going to focus on the direction due to the Coriolis effect that these winds are blowing. Now, the northern hemisphere is broken up. Each of these bands is given a different wind. So these right here are the trade winds. So between 0 and 30 on both sides are the trade winds. Okay, and so these are the northeast trade winds. These are the southeast trade winds. Okay, next we have the westerlies. So the winds between 30 degrees and 60 degrees on both sides are the westerlies. And finally, between 60 and 90, and these are a little bit easier to remember because it's with the North Pole and the South Pole, we have the polar easterlies. And same thing, polar easterlies. So each one of these winds, so this wind belt right here, these are called the northeast trade winds. The winds that blow here, and we're using those convection cells, those are the westerlies. And then up between 60 and 90 degrees, those are the polar easterlies. Now, remember, we have these convection cells, so the air is moving in a circular pattern. So that still holds true. But what we're going to see is that when it's moving along the surface of the Earth right here, so along the surface of the Earth right here, it's not moving in a straight line. Remember, because of the Coriolis effect, that line is actually curved, and we said that in the northern hemisphere, it's curved to the right. So we see that this arrow is coming down here. So instead of me drawing the arrows coming straight down, remember it's curved to the right. So if we're doing it from the direction of the arrow, it's going to be curved like this. Okay, so all across this hemisphere, or this band in the northern hemisphere, the wind is being curved to the right because of the Coriolis effect. Okay, now let's look at this line. This line is going towards the top from 30 to 60. So again, it's still going to curve to the right, but this time it's going in this direction, so it curves that way. So it's still curving to the right in the northern hemisphere, but it looks like it's going the opposite direction because we started at a different point. So here we were moving up, here we were moving down. And then the last one, we follow this arrow. So this arrow is pointing down, so we go down and curve to the right, go down and curve to the right, and this is symbolic of what our wind patterns look like. So with a convection cell, it's not moving in a perfect circle like this. It's actually curved as it does it. Now we can continue to draw these winds. So I'm just going to draw the convection cells in the southern hemisphere as well. So remember, it's always easiest to go with the middle lines here to get the next line. So that one's going down, so the one next to it has to go down. And so it goes like this, rises. Okay, this one's pointing up, so this one has to point up as well. It goes over, down, and over. Good. Now in the southern hemisphere, remember the winds curve to the left. So this arrow is going up, but we're going to curve it to the left. So it's going to curve to the left, curve to the left, just like that. Now this arrow is going down, so this one is going to go down, but remember it's from the direction of the arrow, so it's curving to the left. So again, imagine that you're right here. If you were driving in a car going this way, if you turn left, it would be going in that direction. So turn to the left, turn to the left, left, left. And then finally, this one again is going up, so you're curving to the left and curving to the left. So that is our global wind patterns diagram. You'll want to refer to this when you're doing your notes. Sorry, your classwork on global winds diagram, because you'll be using this, or you can use this to solve that and finish that assignment later on. Here's a picture of our convection cell again, but now we're going to look at this diagram and we're going to look at how it influences the pressure belts. So here's the surface of the Earth right here. There's the surface of the Earth. We have sunlight that comes in, so it's coming straight in. So here's the sunlight. Now the white, what I'm going to use with the white chalk is going to show the air patterns. So as this air right here at the equator gets heated up, we've already talked about that hot air rises. Now when hot air rises, that is going to create a low pressure system down here at the bottom. So down here, this creates a low pressure. So think about it like a vacuum. This air right here, so this air is getting sucked away from the Earth, so it's like a vacuum, so there's low pressure down here. Well, now up here, because all the air is being pushed up this way, so all the air is being pushed up that way, it's actually going to create a high pressure system. So anywhere where the air is being pulled away, then that creates a low pressure system. Anywhere the air is being pushed, that creates a high pressure system. So as the air goes around in the convection cell, what we are concerned with is what the pressure system looks like on the Earth. So we've already established this one right here. There's a low pressure system. Now over here, again, because the wind is being pushed down, it's pushing down. So this right here would be a high pressure system. So now we've already talked about this earlier, is that wind moves from high pressure to low pressure. So this is high pressure, so the wind is going to move from high to low, and that drives our convection cells. So we're kind of putting everything together right now, that we have low pressure because the air is rising, it moves over here, and then as it starts falling back to the Earth, it's pushing down. So kind of like an air compressor that pushes air out, it's pushing air down. It creates a high pressure over here, and then that air continues to move around and around, and that drives our convection belts, or our pressure belt. Okay, so if we look at this diagram, and we'll be making a diagram similar to this in just a minute, this shows how the Earth has various repeating patterns of low pressure and high pressure, and we'll look at this in just a minute when we go back to our diagrams in the notebook. Okay, give you guys a little chance to reflect on this. Here's a quick check. So what is the difference between a pressure belt and a global wind belt? So the first part of the notes we talked about the global wind belts. Now we're talking about the pressure belts. So look over your notes and answer this question. And before you do that, I'm going to give you 15 seconds to think. Okay, go ahead and share this with your partner. Okay, and let's continue on with the notes. Okay, turn to your interactive notebooks, and now we're on page 37. This diagram is going to be very similar to the one we just drew. So take out your notebooks, turn to page 37, and be ready to go. Alright, we are going to start by drawing the start, or the at least the very beginning part of the diagram we had last time. So again, we want to draw the Earth, take up a significant portion of your space here. It's not very circular, but you get the picture. Let's start by doing our bands. So first we have the equator, and this is 0 degrees. Then we have our 30-degree band. We have our 60-degree band. Remember, these are north. And finally, we have our 90-degree north. Then we could redo them down here. we have our 30 degrees south, our 60 degrees south, and then finally we have our 90 degrees south down here at the South Pole. Okay, next I'm going to again show you where the pressure system is changing. So we have the sunlight that's hitting right here. So I'm going to draw my convection cells over here. Because sunlight is coming right here, the temperature is rising, and so the hot air rises like a hot air balloon. And so I'm just going to quickly draw our convection cells again. So you can draw these. They should go all the way around, so each hemisphere should have 3. So you can draw it with me, or you can go ahead and draw it on your own. Just make sure you're following the same pattern. Okay, that's the northern hemisphere. For now, we'll just leave those. We won't do any on the southern hemisphere. And so now we're going to look at the pressure belt. Remember, anytime the air is moving away from the earth, that's creating a low pressure. So as the air is being pulled away from the earth, so in this region right here, remember this is where you have what looks like a vacuum. The air is being pulled away, so that creates a low pressure system right here. And then as we go around, the air starts moving back towards the earth, so that creates a high pressure system in this region. So we have a low pressure and high pressure. And then we go over here, again the air is being pulled away from the earth, so that creates a low pressure. And finally down here, or up here in the North Pole, where the wind is being pushed back down, it's creating a high pressure in this region. So if we went ahead and labeled it on here, this entire band all the way across at the equator, that is a low pressure. So we have low pressure, and then basically it just alternates from low to high to low to high, all the way up and all the way down. So we can go ahead and fill this in. So this is high pressure here, low pressure along this band, and then high pressure at the North Pole. And then we can go ahead and do the same thing for the southern hemisphere. So we have low pressure at the equator, high pressure on this band, low pressure on this band, and again high pressure here. And again, those pressure differences are all caused by whether the air is moving away from the earth or towards the earth. So low pressure, every time we see low pressure, the air is actually moving away from the earth, so it's moving up and away. Whereas for the high pressure, the air is moving down towards the earth. Okay, so that's what creates the difference between the high pressure and the low pressure belts. Now, each one of these belts actually has a name to it. So the one at the equator, these are actually called the doldrums. So those are found at the equator. At the 30-degree mark, so on both sides, these would be the horse latitudes. Okay, and then we could also put horse latitudes down here. The 60-degree belt, these are called the subpolar lows. So same thing in the southern hemisphere. And then finally we have the polar highs. So up here would be the polar highs. And the high and low just are referring to the pressure. So again, down here we have the polar highs. And those are the names of the actual wind belts at each latitude. So 0, 30, 60, 90. 0, 30, 60, 90. So one more time, we have the doldrums at 0, horse latitudes at 30 degrees on each side, subpolar lows at 60 degrees on each side, and finally the polar highs at 90 degrees on each side. And those are the pressure belts. Alright, so back to the notes. Here's a little quick check for you to show me what you know. So the question, explain why some areas have high pressure belts and why some areas have low pressure belts. So some words you might want to include in your definition have to do with the densities or the convection cells or the movement of air, but make sure you explain to me why there are high pressure belts and low pressure belts. So go ahead and take 15 seconds to think about it, and then I'll have you share with your partner. Okay, go ahead and share with your partner. And all right, let's get back to the notes. Okay, this last section is going to go fairly quickly. We won't discuss this too much. We have local winds. So at this point, we've been talking about global winds, meaning winds that are over the entire Earth. But we also have local winds, which happen at a smaller scale, and those are mainly influenced by the local temperatures. Okay, and last thing, we have two concepts that are related to each other. We have a land breeze and a sea breeze. So the land breeze, we have air that flows from the cool land to the warm water, and this usually occurs at night. And then we have the sea breeze, which is similar, but with a sea breeze you have cool wind that moves from water to land, and this usually occurs in the afternoon. So I know we went through this kind of quickly, but we'll explain this in the diagram on the next slide. So here's the difference between a sea breeze and a land breeze, and you'll want to know the difference of these. So we'll go through it and we'll explain it. So make sure you put a star by these and by this diagram because you want to know the difference here. So in a sea breeze, we have the cooler air right here. So it's cooler because it's right on the ocean. So the water cooled off overnight, so it's cooler. And then it's hotter over here. So during a sea breeze, the air flows from the cooler ocean to the warmer land, and it keeps circling around like this. So with a sea breeze, it starts with the sea or the ocean. So we know that the sea breeze starts on water, and the water is cooler during the day because it cooled off during the night, and so it moves from cooler air in the sea to warmer air above land, and it goes in this circular pattern. Land breeze is very similar, but it's the opposite. With land breeze, remember the term before the breeze tells you where it's starting. It's a land breeze, so the air is starting above the land, and it's moving off. So now because this is nighttime, the land is actually cool, and the water takes a while for the temperature to change, and so the land is cool at this point. So the air that's above the land is cooler, so the cooler air is going to flow over the ocean, and then it follows a circular pattern again, and that's what a land breeze is. So just to review these two, a sea breeze, the air starts above the sea. Land breeze, the air starts above land. Now in both cases the temperature stays about the same. So during the day, the land, so on the left, so we're looking at the daytime right here, the land is warmer, and so air is flowing from the cooler sea to the warmer land. On a land breeze, this happens at night, so because it's nighttime, the land is cooler, and it's a land breeze, so the air is flowing from land, and so it's flowing from the cooler land to the warmer water, and it's going around in that circular pattern, and that's the difference between a land breeze and a sea breeze. Okay, that's it for today's note, so go ahead and take out your classwork, and you may begin working on your classwork.